My name is Mohamed Muddassir and I'm a postdoctoral fellow at the Science Lab at the Hong Kong Polytechnic University, and I'm very happy to present my ongoing research in this symposium. The title of my presentation is Automating the Tower Crane, Integrating the Development and Simulation of Path Planning and the Trajectory Tracking of the Tower Crane in Life. With a bit of science jargon, we want to investigate the feasibility of using existing robotic tools to develop the algorithm needed to automate the tower crane operations. For example, path planning for transporting the payload and the trajectory generation based on the planned path, and regulating the motion based on the planned trajectory. The core components needs to ensure the motion awareness of any robot or system needs a planned path, and the trajectory can be generated while respecting the dynamical and the physical constraint. In the last, the controller ensures the physical system can shift from the current state, in our case which is the position of a payload in tower crane, to the desired state while following the planned path and trajectory. The existing literature related to the tower crane, mostly the path planning, trajectory generation, and the control are reported and considered as a separate problem, without interchecking the feasibility of the planned path with the controller and vice versa. Similarly, the input of the sensor observing the construction site is not actively included in the path planning. Instead, many researchers include the BIM or CAD models for this purpose. Also, the validation methods used for path planning, trajectory planning, and the controller are mostly confined with the simulation of the dynamic model of a crane, or using the physical miniature version of the tower crane, which can capture a bit of the kinematics of the tower crane, but cannot capture the complete picture of our. So to develop a framework which can cater the needs and existing limitation in automating the tower crane, we propose a development framework using AROS. AROS is a robot operating system which offers the basic algorithms to develop the robotic system ranging from the high-level decision-making, fleet management of multiple agents, down to the collision checking, path planning, and trajectory generation, even more lower to the lower-level hardware interface. So, using this framework, we develop a real-scale 5-degree of freedom kinematic model of a tower crane, which includes the jib trolley and the hoisting mechanism as actuated joints, and we have modeled the traditional and the radial springs as the unactuated joints. To achieve this, we have developed a URDF model of the robot, which is a configurable robot description, which can include the kinematic links and the joints with the physical properties of the system. So this developed tower crane model is then included in a physics-based simulation, the Zoubeir, which is a simulation engine to simulate the motion of the physical system or the robot while considering the real physical parameters like collision, gravity, wind speed, and the direction, also the friction and the damping between the joints or the body. The Zoubeir also offers a variety of simulated sensors like camera, LiDAR, force sensor, torque sensor, and also the actuators for linear actuators and the revolute motors. Besides these, we also have constructed the construction site in the Zoubeir model, and then use the simulated LiDAR sensor in the simulation, so we can keep monitoring the construction site in the real. So now let's talk about the methodology. Our proposed framework is based on the ROS, in which under the hood use the MOVIT, and MOVIT provides a very solid and backward kinematic solver, and all of these solvers can be generalized based on the robot description. Further, the LiDAR sensor points out can be routed to the MOVIT to define the occupancy grid. So occupancy grid is a representation of a 3D space to show which grid of the space is free to move and which one is obstructed, which helps the path planner to plan the collision-free path in the obstructed environment. The jib and the trolley controllers were developed, and as they are coupled with the direction and the radial swings, so we have, as each of these controllers would be responsible for controlling 2 degrees of freedom, where the 1 degree is only actuated, and thus at the end the gazebo will be responsible for simulating the sensor, tower crane, and charting each step of the simulation. So to operate the tower crane in the automatic fashion, path planning and the trajectory planning is the initial step to get the reference motion. As the tower crane is under actuated system, as the 2 out of 5 joints in a dynamic regions are not actuated, thus the controller for the under-actuated joints needs to be developed. We can start developing the control by interpreting the dynamics of a tower crane as a mathematical model, which we adopted from the Umar et al. We can draw the dynamics by the Lafhaj method, where we just need the kinetic and the potential energies of the payload in the trolley And using the Lagrange framework, we can come up with the equation of motion for each degree. To drive the controller, the drive equation of motion are complex and highly coupled with each other. To drive the controller, this LQR controller, we need to linearize the equation of motion and divide to achieve this, we have divided the system into the two subsystems. So during the linearization of the system, we assume that the small swing angle considered the parameter of each subsystem as time varying and ignore the derivative of the total variables in each subsystem, resulting into a simplified subsystem where the KC controller for the position of the trolley and minimizing the radial swings will be drawn from subsystem 1, and the controller K gamma, which regulates the rotation of the hip and minimize the tangential swings, will be drawn from the subsystem. So the input on the trolley effects will be computed, and as the differential current and the desired state multiplied by the gain. The controller for the slew controller generates the input torque for the chip, and whereas the other controller for the trolley produces force, and which will be multiplied by the gain, and then we are computing the gain using the LQR formulation, which is basically an optimization function to compute the optimal gain, and we are computing the optimal gain in each and every control iteration. As our system is a time varying system, so that's why we have to implement the time varying LQR control in order to make sure that we can control the design. So now this diagram shows the architecture of our proposed method. The thought is the real scale diagram in the physics simulation, and the three controllers are the input between the current state and the desired state. And all the outputs of the controls are bounced from the saturation function to ensure that the input to the tower spin system couldn't exceed the physical limitation of the mechanical or physical system. Yeah. So let's see the results now. So here's a demonstration of the video of a real scale tower crane in the construction site, automatically transporting the payload from the blind spot based on the sensor input. On your left is a plan scene which shows the current state of the tower crane in gray and the desired state in the orange color. The boxes around the crane are occupancy grid, and this 3D grid is generated based on the result input, which is the motion tracker. On the right hand side is the gazebo interface which shows the real scale tower crane in the construction site. From the motion, it is evident that a small sway is induced at the start and the end of the transport maneuver, which is due to using the quantic spline. It generates a trajectory which is differentiable in fifth order. Thus, the expression profile in the generated trajectories are not impulsive. Instead, the motions are much more smoother in the start and the end of the frame. So here this result shows the jib trolley and the hook tracking, the tracking of all of these degree of freedom, the tracking of trajectory, and also the input forces and torque and the swing angles. And also you can see that it's evident from the D and J from the both subplots that the swing angles are not changed that much, and which is due to using the quantic spline, which is fifth order differentiable, which makes sure that the acceleration profiles don't have the impulse in it, and all of the acceleration profiles are continuous. So in the term of contribution, the time we have presented the time varying LQR controller for the power crane chip and the controlling and the trolley motion, and we have tried to integrate the power spinning generation and the control in one framework for the development for the testing and validation of the further methods, and also we try to use our simulation work and make a system for the simulation, so it can be tested in the physics-based real simulation. And in the conclusion, there is no direct support available for the under-actuated system in ROS. So in the term of control and the kinematic panel, so most of the existing, so if we can come up cope with this problem, that if we can control the system in ROS using the under-actuated system, thus we can use existing robotic algorithms which are already available in the ROS framework. And the third that using the quantic spline, the generated motion is much more smoother if we are not considering the quantic spline as compared to the and I'm really happy to answer any question during the Q&A session, and thank you so much.